Okay, yeah, and then I'll talk about furniture. Okay. All right, so first, we will not be having class on Thursday. Thursday, I will be traveling to Starkville to give a talk at Mississippi State the next day. So during class time is when I need to be on the road for that. Okay. So today we're getting to a new chapter, which is actually the last chapter that I have in the notes. About time-dependent problems. Spend so much time on equations like Poisson's equation. So how do we handle time-dependent problems like heat equation, wave equation, things like that? And the basic idea is we're having to discretize the PDE in space and time. And you already know how to do that in space, for instance, using finite differences or spectral methods. And so we would still do that. But now we have to discretize in time also. And that means dealing with using time-stepping methods for solving ODEs. And so that'll be my focus here. Okay. So a problem we're going to look at is we'll stick with first order in time, but we may have PDEs that are, of course, higher order in time, like a wave equation. So we have so d dt is equal to LU, and I'll explain what L is in a little bit. We have some interval in time, and then we have an initial condition. All right, so this is the PDE. These are the IC, or initial conditions. And then we have, like before, boundary conditions. So in this example, let's stick with Dirichlet. So U is equal to some function G, which might be 0. Okay. Where X is on the boundary of omega. Okay. So all of this together is an IBVP, initial boundary value problem. Okay. So here's some examples of the operator L. The most straightforward one you've seen most often, is Laplacian. So if I fill in the Laplacian here, we would just have a heat equation. But some other examples. Operator L is equal to, or LU, the some vector B, dot product with the gradient of U. And we did see that some time ago regarding the wave equation. So here we have so we have first order derivative in time and first partial derivatives respective spatial variables that leads to advection, where you have like a wave propagating in like in one direction. Okay. Why settle for one Laplacian when you can have two? So if you do minus Laplacian of Laplacian, so this is a biharmonic equation. Well, by itself, this is a biharmonic equation if it's just like Laplacian to Laplacian of u is equal to 0. But if we pair that with du dt, this leads to the beam equation. Oh, wait. So I need to correct that. If we have utt, that leads to the beam equation. All right. The Laplacian has negative eigenvalues. So then we can have, when you have ut is Laplacian of u, your solution features exponential decay. That's a well-posed problem. If I had a minus here, that would be backward diffusion minus Laplacian has positive eigenvalues. We'd have exponential growth. But because Laplacian has negative eigenvalues, you apply it twice. That's positive eigenvalues. That's why we need the minus here if we're going to pair it with ut. So again, you'd have exponential decay. So that minus is needed for well-posedness. But that is not the beam equation. You need utt to make this beam equation. Okay. And then one more. LU is probably an unfortunate choice of letter there. F times a norm of a gradient of u. So it'd be square root of ux squared plus uy squared plus uz squared if you're in 3D.
Dr. Lambert, can you tilt the screen?
Sorry, what?
Can you tilt the screen, please?
Oh, dang it.
Thank you.
Okay. Now, when you pair this with ut, you get what's called the level set equation. Okay. And the level set equation is for tracking how the interface between two substances moves over time. For example, an object embedded in a fluid. And where u is equal to 0 marks the boundary of a fluid. When u is non-zero, that'd be like the distance from a point to the interface. So if you're modeling how the object and fluid interact with one another, like the object moving from a fluid, this PDE can be used to solve for that, and the solution would be the interface changing over time. And because the object is defined by where u is equal to 0, that is a level set of u. So whenever a function is equal to a constant, that's a level curve in 2 dimensions, or level surface in 3 dimensions, but in general, a level set. So there's a whole family of methods called level set methods that are, I won't really get into that, but they're useful for solving these kinds of problems. And yes, Chelsea, but it's one of the things I was talking about in our meeting yesterday. So, okay. Oh, I'll take you to use on my phone. All right. Okay. Now, if you let ut go to 0, or if you just set it equal to 0 in the PDE, then you go ahead and solve that time-independent problem, and that will give you the steady-state solution. So for problems where the solution is evolving over time, but eventually converges to something, that is a steady-state solution. And because it's converging, it's not changing over time anymore. ut would have to be 0. So you can set that equals 0 at the outset to get an idea of what the steady-state solution should look like. Okay. So as an example, suppose you have a heat equation. UT is Laplacian of U. So steady state solution satisfies Laplace's equation. Or if I have a source term, UT is equal to Laplacian of U plus F. Steady state solution would be a solution of Poisson's equation. Where so minus Laplacian of U is equal to F. Okay. All right. Now, here I focused on equations that are have a first order derivative in time. But if you have a PDE featuring a higher order derivative with respect to time, you can always rewrite it as a first order system. First order system. So as a simple example, UTT is equal to UXX can be written as UT is equal to VX, and then VT is equal to UX, because suppose I look at UTT, I take a derivative of this equation with respect to t, and I get VXT. But then I can take a derivative of this equation with respect to x, and I get the same thing, VXT here on the left side, which would be equal to UXX from the right side, so then UTT equals UXX. And then there's a standard approach that you probably learn in ODE classes for rewriting a higher order system of a higher order ODE in terms of a system of first order ODE. So we can use that here. So for that reason, I'm just going to focus on problems where we have problems of this form. First order time derivative is equal to some spatial differential operator, which also could be a system. So U could be a vector valued quantity. So another form of a wave equation. So U and UDT with respect to time is equal to 0, identity, L, which could be a Laplacian. I'll just write Laplacian, and then 0 applied to U and UT. So if you were to write this out, I'd have UT equals UT, where I is the identity operator, and then UTT equals Laplacian of U. So here I have VT, which is a vector, is equal to this operator times a vector V. So again, you can always write it as a first order system. So as far as numerical treatment, I'm going to stick with the first order in time case. All right. Okay. Questions about anything on this board? Okay. Oh, I see we have a half eraser again. Oh. We do a full eraser. Let's see if it works. Not that great. I don't know. This feels so weird. notes go? What the hell? Oh, okay. Like, I know I had them open here. I didn't close them. Okay. Now, all right. So as I said earlier, once you have a time-dependent PDE, it discretises both time and space. Which do you do first? And you do either one first. So the usual approach is to discretize in space first. And that is called the method of lines. Okay. So the idea is your solution, u of xt, becomes a vector u, where the elements of u are the values of the solution at selected grid points that may or may not be equally spaced. And then the differential operator L becomes some matrix A. So then the PDE ut equals LU becomes a system of ODEs. U prime equals AU. And because the PDE I've written here is linear, the system of ODEs that comes from it by spatial discretization is also linear. And that's the approach we're going to focus on, because then you can use whatever methods for solving systems of ODEs on this system. Your Morgan-Cutter methods, multi-step methods, things that I'll get into, well, not Thursday, but next week. Okay. So that's the method of lines approach, where a line corresponds to a particular grid point, like an X value. Because each one of these systems of ODEs comes from describing the PDE at a particular point in your domain, an X, so some X in your domain omega, and then you're replacing any spatial derivatives by some approximation, like a finite difference formula, or using a spectral method, something like that. Okay. The other possibility is time first. Okay. So you replace ut by some, like for instance, a finite difference formula. So in this case, I'll use a forward difference. Okay. So then your PDE ut equals LU becomes this, that your solution at the new time is approximately equal to the solution at the previous time plus delta T L u of xt. So at this point, this is still the original operator L from the PDE. Now, you could then choose to discretize this. So a lot of cases, like you can arrive at certain numerical methods or PDEs by discretizing first in space, then in time, or in time, then in space, and arrive at the same result. It just depends on which approach you're using to discretize in space and time. But what if you have some way of applying the operator L exactly? Then you have no need to discretize in space. So for situations like that, that'd be one good reason to discretize in time first, or maybe in time only. But generally speaking, we use method lines. And so that lets me focus on how to solve systems of ODEs. What methods are used for those? Because this discretization has to already account for boundary conditions. You'll still have an initial condition, u0 is equal to u naught, some vector u naught. So you still have an initial condition that is a spatial discretization of the PDEs, the original initial condition that you had from the initial boundary value problem. But how you discretize in space, like what finite difference formulas do you use or whatever other method you use, has to take the boundary conditions into account just to get this far. Right. Any questions here before I get into ODE methods? Okay. Come on. No, I don't want to pay for something. I just want to look at my damn notes. Okay. It's weird. I turn away from my notes for like a minute, and it takes you back to the first page. Okay. Now, you may have seen time-stepping methods for ODEs in another class. Actually, the class where I normally teach about these things is Math 561, which you've taken. Not everyone has taken into class, but majority. But again, I don't assume any of these things. Okay. So the problem we'll consider is the general first order ODE or system of ODEs that comes from some PDE. And everything here, like y and f, are vector valued to allow for this being a system. A lot of ODE solving methods apply pretty much the same way, whether it's to a single ODE or a system. Okay. So I show some simple time-stepping methods, and we'll get to more elaborate ones next week. So first we have explicit, also known as forward, Euler's method. Euler, not Euler. Years ago, I was watching a TV series, which was actually based on some books that I fairly enjoyed. The TV series was called, I don't think it's still running, Rizzoli and Isles. And Isles, her character was a scientist, mentioned what she actually said was referring to Euler's formula that relates the three most important numbers in mathematics. So screenwriters did not realize that it's actually Euler's formula that relates to five most important numbers in mathematics. E to the I pi plus 1 is equal to 0. So I just sort of gave up on Hollywood after that. It's like, you can hire consultants for this. In Google Hunting, they hired a math professor to write real math on the board, just so Matt Damon's character could look good. But yeah, like, at this point, you guys aren't even trying. Okay, so but whatever. It's also known as this Euler's method, but it can be known by any of these things. So all you're doing is you're replacing y prime at time tn with a forward difference at the time tn, where tn is n times delta t. So we're assuming a fixed time interval. So these methods do not compute a formula for solution as a function of time, but at a certain selected time, t1, t2, t3, etc. Where t naught is just 0, that's where the initial condition holds. Okay, so to get from a solution at a certain time to the solution at the next time, so dy dt, or y prime, is supposed to be equal to f at that time. So the actual method is yn plus 1 is equal to yn plus delta t f of tn yn, where y sub n is our approximation to the exact solution at time tn. So when discussing numerical methods for ODEs, when we say y of some time value, that's always in reference to the exact solution. When we have y subscript, something where subscript is an index of a time value, that always refers to the computed solution. So exact computed. So the computed solution satisfies this. So this is how we perform time stepping or time marching, starting from the initial condition and then computing y1, y2, y3, which approximate the solution at times t1, t2, t3. Sorry, I kept getting in the way. All right. Okay.
So you said y of cn is the exact solution?
Yes.
And then y sub n is the
Computed solution. So when describing a numerical method, we have to refer to the computed solution. But then later, when we deal with error analysis, we'll actually substitute the exact solution into the numerical scheme for local truncation error. Okay. All right, so that's explicit or forward Euler. We also have implicit or backward Euler, which is the same thing, except instead of using a forward difference, we at time tn, we use a backward difference at time tn plus 1. So the method looks almost exactly the same, except f is evaluated at time tn plus 1. Okay. So this is from y prime at tn plus 1 is approximately so the difference quotient here is exactly the same as there, but here it's playing a role of a backward difference rather than a forward difference, because look, we're evaluating a derivative. Before it was at time tn, now it's at time tn plus 1, and that must equal f at time tn plus 1 rather than time tn. But notice here we have yn plus 1 on both sides of the equation, so it's passed into f. So you have to solve for this. Now, if f is a linear function, that's easily done. You just rearrange. But for general f, you need to use some iterative method, like some sort of root finding method, like Newton's method, to solve for yn plus 1. So that's the difference between an implicit method and an explicit method. Explicit method, it's plug and chug. You have your solution at the previous time, just plug it into the right side, and out comes the solution at the new time. But you can't do that here. You need some initial guess. For example, it'd be perfectly fine to use yn as an initial guess for yn plus 1. Or maybe this, you can compute this, and that is an initial guess. And then you can like substitute that in here, like a fixed point iteration. And so there's different iterations that you can choose to solve for y at the new time.
I have a quick question.
Yeah.
So for the formula you wrote for the backward difference,
Yeah.
you had tn plus 1. On the forward difference, you had tn plus delta t.
Oh, they're equal because of that.
Tn plus
Yeah. So
tn plus 1 plus 1 delta t.
yeah. So tn plus delta t which is t sub n plus 1.
Yeah, so what makes this formula backward difference?
Because of what we're approximating. Here we're using this difference quotient to approximate y prime at tn.
Okay.
And therefore using a point that comes after it. Here we're approximating y prime at tn plus 1 using a value of y from before it. Okay. I know it's kind of weird, but I won't get into too much of the iterations for implicit methods now, but one point worth making though is normally when you're solving an equation like this by iteration, you would keep iterating until it converges to some small tolerance, like 10 to the minus 10 or something. But you may not really need to do that here because because we've already discretized in both space just to get the system ODEs, and then in time to get this, there's already some error involved. So if there's already some error just to get to this point before we even start solving this equation, then there's no need to keep whatever iteration you're going to use. There's no need to keep using that iteration to converge to a really, really small tolerance when that error is negligible compared to whatever error you already have from a discretization. So a lot of times when people use iterations in conjunction with an implicit method, it might just carry out only one iteration. If you have a really good initial guess, you probably don't need, and you can get a good initial guess, you don't really need to do anything more. And that's important because the fact that you have to solve an equation like this at all, that makes implicit methods possibly a lot more expensive than explicit methods. What we'll see later is that a virtue of a benefit of implicit methods, so you can often get away with a larger time step than with explicit. And that can offset the extra computational expense. But it turns out that if you're using these iterations to solve this equation, if you're using them wisely and take into account your other sources of error, really the implicit methods aren't really that much more expensive necessarily than explicit ones. It depends on the problem. I need to give that disclaimer. There are some problems for which, depending on the function f, for which an implicit method can be extremely expensive. But it's just something to keep in mind on a problem-by-problem basis. Any other questions about these two methods? Okay. So what I'll conclude with is some convergence analysis. At least for the simplest method of all, explicit Euler, just to acquaint you with the concepts of convergence analysis that can be applied to to other methods. Because when we did a Poisson's equation, we learned about local truncation error, global truncation error, and what it meant for the numerical method to be consistent and stable and convergent, and how the method is consistent and stable and it's convergent. So these same ideas and the relationships between them also apply to these kind of problems. It's that you have to define everything appropriately for this kind of problem. Okay, you're kind of over me time for lasers. They work well, but dang, it takes a long time. Okay. Stop reverting to the first page. Okay. So that's a great job, Joe. All right. Let's take a look at convergence analysis. So local truncation error is defined as an analogous way to how it's defined for time-independent problems like Poisson's equation or boundary value problems. Local truncation error in whatever problem you're applying it to is always about substituting the exact solution into the numerical method. So the local truncation error at time tn, so that's a subscript n, is equal to, in this case, substituting the exact solution at time tn plus 1 and tn over delta t minus f. Okay. Now, as I said, you're substituting the exact solution to the numerical method, but notice that the numerical method underwent some algebraic rearrangement. So if I write down, I repeat Euler's method in its usual form, okay. So what I did is first, you're putting everything on one side, set equal to 0. The other thing is you divide by delta t. So that's very important. That and it's a convention to define local truncation error this way. That you divide by delta t. And the reason for that is for describing order of accuracy. Because what we'll see is if we define local truncation error this way, and we find the order of accuracy locally, like the local truncation error, that the same order of accuracy will apply to the global error. We want those to be the same. If I did not divide by delta t, it would be different, and that's something that can cause confusion. Okay. Now, in this case, we actually know, because y is the exact solution, we know what this is, by Taylor expansion, that this is equal to delta t over 2 times y double prime at some unknown time, squiggly. Okay. And this comes from Taylor expansion of y of tn plus 1 around Tn. So time Tn is the center of a Taylor expansion. So I won't go through details of all, but if you substituted the Taylor expansion in here and simplified as much as you can, keeping in mind that y is the exact solution. So y prime is equal to f. Then everything cancels and you're left with this, which is the Taylor remainder. Okay. So this right here is the local truncation error. All right. So the local truncation error is order. Ooh, mistaken the notes. I had h. I've been using delta t everywhere. Or delta t. So it's because it's delta t by itself to the first power. So this is first order accurate. So not great. But what do you expect from such a simple method? Okay, so that's the local error. The global truncation error is defined in a similar way as for Poisson's equation. I'll call that capital E n. And that is equal to the exact solution at time Tn minus Yn. Oh, I see the notes I had these as superscripts, here they're subscripts. Oops. All right, I'll just be consistent with what I write on the board anyway. Okay. Now, so if I write out what this is, at least not at time n, but time n plus 1. So that would be y of tn plus 1 minus yn plus 1. But now what I can do is I can substitute Euler's method in here. And I can also use this relationship and substitute, like I can take this equation and rearrange it to isolate y tn plus 1 and substitute that in here. So once I do all that and simplify as much as I can, then what I would get is, okay. Let's see, actually maybe, I'll go ahead and carry it out. So ytn plus 1, if I rearrange this equation, it's going to be equal to y of tn, okay, plus delta t f at tn y tn, okay, plus delta t local truncation error. All right, so that comes from the yn plus 1 part. Then I substitute in Euler's method. Yn plus 1 gets replaced with all this. Okay. So now to simplify all this, y of tn minus yn, that is the global error at time n. And then I have plus delta t times this difference of f values, one involved at the same time, one involving the exact solution and the other the computed solution. Okay, plus delta t times local truncation error. Okay. So now we have a relationship, a recurrence relation between the new global error and the previous global error. Okay. Now, all right. Now, I'm going to make an assumption here about f. I assume f is Lipschitz continuous in the y variable. So what that means is the norm of f minus evaluated two different y values, but the same t value, is less than or equal to some Lipschitz constant, which I'll call capital L, times the difference in y values. And capital L is called the Lipschitz constant. So then, what I can get from that is, well, here are the two y values in question, the difference between those. That's En, because it's exact solution minus computed solution. So now I can say that the norm of En plus 1 is less than or equal to 1 plus delta t L times the norm of En, and then we still have this local truncation error term plus delta t norm of Tn. So the 1 comes from this, and then the delta t L comes from this with the Lipschitz condition applied to this difference of f values. And the difference of y values is just, it's this, En. So now we have a recurrence relation as simple as we can get between the global error at time Tn plus 1 and global error at time Tn. Okay. questions up to this point? Okay, a few more steps to go. Actually, I'll leave that last step down there. Because now what we have is recurrence relation. I want to express the error at whatever time in terms of the initial error, like E0. That will enable me to get a bound for the global error at any time. And I want to know that as delta t goes to 0, that this error is going to 0. And that would be convergence. Okay. Now, I'm going to define capital M to be an upper bound on the domain of space, temporal domain of our problems. We're considering only time values between 0 and capital T. And we need a bound on y double prime. So we're assuming that, for convenience, we'll assume that y is solution, exact solution y is twice continuously differentiable to be short of a maximum. Okay. So then, if I apply this recurrence relation repeatedly, like here I have En plus 1 in terms of En. But if I replace this with a similar relationship in terms of En minus 1, and En minus 2, I keep going, then this is what I end up with. That norm of En is less than or equal to 1 plus delta T L raised to the n power E0, the initial error. But we don't have any error of the initial data, so that part's just going to be 0. Plus delta T as a sum of powers of I plus delta T L is the I power times the local truncation error at each time. That just comes from applying this recurrence relation repeatedly, and this pops out. So if you were to try this to look at, for example, E1, E2, E3, all in terms of E0, this is what you get. So now we have this relation, this a closed form expression for the error at time Tn. Now, what we have here is a geometric progression. This is a partial sum of a geometric series. So we have a formula for that. So, okay, so we're still going to have delta t. And then the local truncation error, recall that the local truncation error is delta t over 2 times the second derivative, which is bounded by m. So this is a bound in local truncation error right here. This delta t over here. And then the formula for the sum is 1 plus delta t L raised to the n power. So it's this power plus 1 minus 1 over 1 plus delta t L minus 1. Okay. All All right, so then what happens, we could do some simplifying. Like, okay, the ones cancel. Then we have delta TL, but this delta T will cancel that delta T. So now what we have is M delta T over 2L, and then we have this numerator here. Okay. But the expression inside parentheses here, this is the first two terms of the Taylor series for the exponential. So I could say that this is less or equal to M delta T over 2L, e to the L delta T n, or actually n delta T, minus 1. But n delta T, that's Tn. But Tn is bounded. Tn is bounded by capital T. So this is less or equal to M delta T over 2L e to the L capital T minus 1. So now we have a bound on the global error. It's not a sharp bound by any means. At whatever time in our spatial domain. And the key thing here is this factor of delta T. Now we see that this is big O of delta T. So as delta T goes to 0, the error, so the difference between the exact solution and computed solution at any time T in our time domain is going to 0. So we can conclude from this that we have convergence. Okay. Okay. Now, this is a bit of a pain on out of time. It is for simplest time-stepping method. For more advanced time-stepping methods, you don't carry out this direct proof of convergence, but we have consistency. Is a tau n, the local truncation error goes to 0 as delta T goes to 0. Okay, so that's a definition of consistency. And we also have a notion of stability that is a bit much to get into now, but basically the method satisfies a Lipschitz condition. Now, Euler's method is such a simple method that all it took was for F to satisfy the Lipschitz condition, and therefore Euler's method also satisfies the Lipschitz condition. But for more elaborate time-stepping methods, there's a bit more work to do to show that the numerical method satisfies the Lipschitz condition, assuming F does. And then you can say that the method is stable. And then, so that's what leads to this constant L here, which would be different for different methods. And so it can be proven, has been proven, that if a method of this type is consistent and stable, then it is convergent. Just as what as we saw for time-independent problems like Poisson's equation. So there's always that relationship. Okay. Next week, so on Tuesday, we'll get into different, more sophisticated time-stepping methods. And so also next Tuesday, since it's like 2 to 12 time a day, thanks to the printer, I'll see how everyone's doing on the homework, since we're not too far from the end. Which can be both a good thing and a bad thing, I guess.
Bye, Dr. Lambers.
Yeah, bye.